Hi there, this is again Sashank Veligati. I am showing a demonstration of my landscape rendering and the landscape rendering techniques that I have learned and practiced, including level of detail and custom culling. And then I will conclude with the finale of my inverse kinematic spider, which I'm showing here. First, let's go over the landscape. We are rendering a few million triangles here, as you can see in the mesh vertex, the vertices here. What I'm doing is calculating the distance from the camera to the land point, and rendering either lower or higher quality meshes based upon that distance as the need arises. What you will notice is that heavily detailed features of the land are automatically raised slightly to have a higher level of detail, and flatter areas such as the ocean, of course, are lowered just a little bit by deference to have less features. I'm going to go ahead and pause the level of detail for a moment, and you will see that what I have enabled here is a stitching algorithm. This is the kind of thing that you would find really common in terrain engines, where the landscape polygons need to be stitched from the lower level of detail to the higher level of detail. So you can see here there are squares of, say, length 2, and here there are squares of, say, length 1, and then here there are squares that are of length 1 on the left side and of length 2 on the right side. The vertices to calculate these are all done algorithmically in about a page of, maybe 1 page of code, to get that kind of stitching done in the vertex buffer on the graphics card. And so if I can enable level of detail again, these vertices swap in and out using index buffers on the graphics card to show the appropriate level of detail based upon the inherent detail of the land and the distance you are away from the land. So as you can see here, we get a nice even visual quality where the landscape appears as if it is highly detailed at every viewpoint, but in fact it is only highly detailed at the points where the camera is close to the surface, and a lot of rendering time is saved by using lower levels of details for things far away. Of course, in addition to this, I have frustum culling, so if I look this way and turn off the frustum, the vast majority of the land disappears. I can do this for this section, and you can see the shape of the frustum take place in front of you. This happens on a three-dimensional level, so I can be anywhere I want, and you can see that the frustum, as I freeze it here, hides away all the polygons, all the meshes that are not being drawn to the screen, saving a lot of rendering power on the graphics card. That's essentially what I have here for the landscape rendering, but I went ahead and took this further from the original assignment to make a personal project, which is an application of inverse kinematics. Now that I had this landscape working perfectly, I used the uneven terrain of the landscape to essentially create a creature that could walk up and down that uneven terrain, and use a little bit of basic trigonometry and optimization problems to create legs on a creature that would automatically conform to the land beneath it. Now, of course, in addition to this, the creature doesn't just simply slide around. I would like to have some animation in there, so I added a little bit of cubic spline interpolation that lifts the legs and animates them forward. So as you can see, this is not a pre-rendered video. I can freely move the spider back and forth, and as you can see here, I have a lot of algorithms going on here at the same time. That was kind of subtle, so I'll show it again. Essentially what happens here is that I press forward, and the spider will attempt to find the next most viable point to place his feet. I'm going to go ahead and turn the spider around here, and as you can see, as a spider walks, and of course I have a pretty simple mesh on here, just the default rocks texture that you have, so as not to distract you from the animation itself. The spider continues to find a point where he would like to put his feet, and then interpolates his legs to get to that point. Notice that the legs are lifted off the ground in a spline, cubic spline manner, and then animate towards the ground point. Another algorithm that you might notice is that no two pairs of adjacent legs move at the same time. What's happening here is that what we would call, and a lot of insects actually do this as well, not just spiders, the tripedal gait, which is a form of walking in biology that ensures that an optimal set of legs are always touching the ground at all times, so that insects and arachnids, of course, like the spider, can maintain perfect balance. And another essential algorithm essentially is another form of the well-known dining philosopher's algorithm, which is also used in threads, where two adjacent philosophers cannot dine at the same time, and that, of course, is a problem of deadlock, which I have had a little bit of trouble with this guy, as certain legs would want to move and take care of all the resources and not give the other legs a chance to catch up. You can see here that there are some troubles with the terrain, with the inverse kinematics, because of extremely uneven terrain. There just isn't a really good point to orient the spider. So there are limitations to the project and things that I would like to work on. But as far as the tuning, the animation, the walk speed, the turning, and as you can see here, when the spider becomes still, he relaxes and moves the rest of his legs to a more optimal position. Really trying to make a lifelike interpretation of how an insect would normally walk over uneven terrain. Even with all these tweaks, I feel like there are a few things I could have done to make it better. Of course, having an actual artist to draw a mesh probably would have been significant. But as a programmer, I think I'll just stick with programmer art and focus on the mechanics of the animation and not of any of the distracting flair. I have a camera system, of course, for my project implemented here, so you can see a turning focus cam that focuses on the spider and shows where he's going. A camera system that can follow the spider anywhere on the map. A back view third-person camera, so you can control and play with it. And then, of course, the normal free cam where I can control wherever I want. This spider and other animations like it are often used in games for RTSs, action games, shooters. Anytime when you want a creature that to walk up and down terrain. I chose a spider because it might have been a little bit easier than, for example, doing a human, because a human has only two legs, of course, but to get the animation exactly right to mimic what you would feel a normal person would do is a little bit more difficult, but I feel like that would be a great project to take this to the next step. But for now, I feel like the spider really does well. I'll just go one more demonstration round, showing how the doom of spider climbs over the mountain and destroys the village down below. So yeah, I've had a lot of fun with this project, as you can tell, and both my professors and classmates feel like this project turned out exceptionally well to show what can be done algorithmically for animations. That's pretty much about it. You can just enjoy watching a spider walk around for a little while. I feel like inverse kinematics could be implemented more in games. It's not always, as well, it's difficult for the production pipeline, as artists are just so much more used to doing pre-can animations, but I feel like they can add a lot of extra depth to games, as you can see things really adapt to the environment as you normally wouldn't in real life. Anyway, that is my inverse kinematic spider. I hope you like this demonstration, and that's it for today. Thank you.